exam results were generally quite good. The average was 86%. Good. So you have the solutions, and take a look at them and see where you miss some things. I think overall, the understanding was strong. Overall, I was glad to see that. There were a few holes here and there, and you can take a look at them and we can discuss them. The same kind of thing will be on the final exam. So it's important to see where those holes were. All right, very good. All right, so let's see where we are. We're talking about electromagnetic radiation. And to find the solutions generally for the general solution, for fields, electric and magnetic field, given the sources, we found as follows. We found them by first expressing the fields in terms of potentials. And in the general case, the electric field is defined by both the vector potential and the scalar potential. And the magnetic field is the curl of the vector potential. And we found that there's led to gauge invariance. Gauge invariance tells us that we can make a transformation on the potentials as such sorry, I should say lambda. And when we do so, the electric and magnetic fields are unchanged. And that's what the term gauge means here. It's a kind of arcane word, but it just means sort of an extra piece that doesn't matter. Okay? So if we make these transformations, we in no way affect the fields, and the forces on the charges and currents depend only on the electromagnetic fields, not the potentials. Okay. And so this equation in particular tells us that the divergence of A is physically irrelevant. Because we can shift it around any way we like by adding this gradient that shifts the divergence of A, and that doesn't in any way change anything because this kind of transformation does not affect the fields. And so choosing the divergence of A is called fixing the gauge, and one way a particular gauge of interest is the Lorentz gauge, which tells us that we set the divergence of A such that when we add to it the time derivative of the scalar potential at C, set it to 0, that's a fixing of the gauge. And that's the Lorentz gauge. And in the Lorentz gauge, I'll just write this down. So in the Lorentz gauge, found that Maxwell's equations told us that both the scalar and vector potential satisfy the wave equation. With the source term. Okay. And we found thus, using the Green's function, we found the solution, the particular solution, the solution that's determined by the sources, which told us that we can find the potential, say the scalar potential at any point in space at any time, given what the charge density is at some other point, but at a different time, weighted by 1 over the distance. And similarly, the vector potential is the integral over the current at the retarded time over the distance, divided by c, where the retarded time is the time at the point of observation minus the time it takes light to go from the source point at x prime to c. Yeah?
Two things. I think you missed a square on the 1 over c for the Lorentz gauge derivation there.
This is
just beneath your hand.
Oh no, in the wave equation. Yeah.
And then the other thing, you commented that the potentials themselves are irrelevant, right?
The potential, the exact form of the potential, I can shift them this way, and that doesn't change.
So I was curious, in quantum, we actually care more about the potentials, right? Because you have like the Aharonov-Bohm effect and stuff like
That's a
that.
very interesting question. I was just thinking about that this morning.
So I was wondering how
Yeah.
gauge invariance relates
Yeah,
to that.
that's a very interesting point. I think, that's a long discussion.
Okay.
And I'd like to say a few words about that. But before I do that, I'm going to do 2 things. One is I'm going to some light. Let me give you guys back, those of you who came in late, because I don't really know what you roughly with everyone else's parents, so I'll come give you your paper. So let's let me do that, because you came in a little bit late. Said who else made it, John? All right. And I just remembered one other thing I wanted to say that I forgot in the announcement, which is to remind everybody about the final exam. And then I'll come to your question, Donna, which is quite interesting. So the final exam will be Monday, the 12th, from 10 to noon. So that's, and the room will be to be determined. Okay. So let me come to the question now, which is interesting, which is that sometimes it is said that, oh, the vector potential is actually a real thing because the phase that we can see in interference between 2 paths of an electron that go around a solenoid where there is no local field. The field outside an infinite solenoid is 0. Nonetheless, there is a phase difference for 2 electron paths that go around the solenoid, and that's called the Aharonov-Bohm effect. And that phase depends locally. The local phase does depend on the vector potential. But the actual phase doesn't depend on the vector potential itself, but depends on the closed loop integral between the 2 phases, which is equal to what? Well, by Stokes' theorem, this is the flux of the curl of A through a closed surface, which depends only on B. So nothing physical can depend on something. Physics must be gauge invariant. It is a misstatement. It only depends on B. B is the physical thing, not A. But we digress. But excellent question. All right, so this is the general solution, and we're done. Bye, everybody. No. So what we are now looking at is the specific case of a multipole expansion, which is very important in thinking about electromagnetic radiation. It's called multipole radiation. And the physical situation we have is one where we have some charge distribution and current distribution that's changing in some ways as a function of time, maybe it's rotating around. There's some origin. The origin could be wherever we like. And there's some way in which this thing is localized in space in some scale d. Okay, it's the extent of the source away from the origin. Okay, and we have some point of observation where we want to find the electromagnetic fields, okay, which we can find by finding the potentials and taking the appropriate derivatives. Okay, so our goal is to find the fields given this source, given rho and j, which are changing as a function of time. Okay, and so there's using the Green's function, the superposition, every point in this source at some point x prime contributes to the field that we see at the point of observation. Okay. Now we did this in the case of statics, but now we're doing this in the case of fluid dynamics. And importantly, there's an additional scale in the problem, okay? So there's d, but now because of dynamics, we have another constant in the problem, which is the speed of light. And the speed of light then determines a distance scale, and that distance scale is related to the time it takes light to go across the sample, okay? Because what we see is there is going to be a distribution of different retardation times across the sample. There's, if we wrote this for a small, I'll come back to that. But there is, because of the fact that we have a distribution of possible retardation times, we have a scale associated with that distance, okay? And so there is another scale in the problem, which is associated with the time scale. So d over c is the time it takes light to propagate across the sample. And the question is that a short time or is that a long time? Compared to what? Whether time is there in the problem. Where there's the time scale over which these things are changing, okay? So there's some rate of change of these sources. And so if I call t the time scale over which rho j change, then we have some comparison between this time and this time. Is it big or small? Okay. So for the multipole radiation, we are looking at two conditions. One, that we are far away compared to the size of the source. Potential spam. Yeah, it might.
Oh, okay.
My wallet was calling my phone, which is calling my computer now. But that does happen sometimes, I do. Anyway, so we're looking at a situation where the point of observation is very far compared to the size of the source. That was what we already did when we looked at statics. But now there's an additional condition that we're looking for multipole radiation, which is that we have a slowly varying system. So that's to say that this time scale is much, much bigger than this. Or equivalently, that C times T is much, much bigger than D. Okay? Now, I'm not necessarily saying how big R is compared to this. We will see different behavior in the fields depending on how far I am away compared to this distance, which is the distance that light changes, that light propagates in that time. And that will determine different behavior, as we'll see, depending on how far away I am compared to the source, compared to this scale, will determine different behavior of the field. Okay? Yeah.
R is that R, X minus X prime?
No, that's strictly R.
Okay. Which R is this?
That's the magnitude of this.
Oh,
Okay, so it's the distance from the origin to the point of observation. Okay, and script R is the distance from a point in the source to the point of observation, but these distances are close to one another to the degree to which X prime is small compared to R. All right, excellent. And so in particular, when we have oscillating sources, we might take T to be the period of oscillation, in which case C times T is 2 pi times C over omega, which is 2 pi over K of a wave that would propagate at that, or lambda. Okay? So another way of stating this multipole condition is that the wavelength of radiation is much, much bigger than the size of the source. Okay? That's equivalent to, this is a specific case of this general case. Okay? So for example, if I had an atom which has an angstrom extent and it's radiating optical frequencies, that radiation is dipole radiation. Well, we'll come back to it. We can do a multipole expansion of the radiation. Okay, so coming back to this, what we said under these conditions, we have that this is approximately R times 1 plus or minus x minus x prime over r squared power 2, divided by 2 is 2, which is r minus r hat dot r prime. So this is the little extra distance that every point here, this is the value of script R. Script R is this minus this little piece, right? We made that approximation. And so 1 over x minus x prime is approximately equal to 1 over r times 1 plus r hat So 1 over the distance from here to here is approximately 1 over r plus a little bit, right? Having to do with where I am. And what that means, as we see over here, is that there's going to be a slight spread in the retardation times So T0 here is the time, the retardation time from the origin. It's my local time minus the time it takes light to get from the origin to me. Okay, that's T0. There's a slight addition or subtraction to the retardation time depending on when the source is a little closer to me or a little farther away from me compared to the origin. And that is the little bit. And so what we then do is a Taylor series expansion of, no, where is it? Of this, right? Under these, we do the Taylor series expansions, okay? Now, it's a mess, okay? And it's a total waste of time for me to derive this on the board for you. So I'm gonna cheat. I don't cheat often, but occasionally, like, well, anyway, I'm not advocating cheating. I'm not advocating cheating. But let me, you know, I maybe I told you this before. You know, when I was a kid and we had a substitute teacher, and the substitute teacher was lazy and didn't have time to prepare the actual lesson for the kids, they would show something called a film strip. Okay? And it was like the strip of film that, like, you know, there's little stories, and it go beep, and then someone pushed a button, and then, so like when you're not prepared to give a lecture, you give the film strip. So here we go. All right, so let's get to it. Okay, so I need to switch this to this, and maybe I do need to lower the shades. Is it too bright? Can you see it okay, folks? Is it okay? All right, so this is what we were just saying about doing this multipole expansion and making these are what we just talked about, all right? So let's, okay, so we make that multipole expansion. This is my 1 over x minus x prime piece. And then we do a small Taylor series expansion around the retardation time. So the retardation time is T0 plus a little bit. And so we get what the source is at that, and then the first order correction. Okay? And the first order correction is the small delta t times the time derivative, just using Taylor series expansion to first order. Everyone, I see some nodding heads. So, okay? And we do the same thing for the current, and we get the vector potential. All right? Okay, so if we keep terms only to first order in the small x prime, the small distance away, we get this expression for the scalar potential. Okay? And what we see is this is the lowest order terms. The first term we recognize as just the monopole term, okay? Gives us potential like that. Then we have terms that have to do with the dipole. We assume in this case that the total amount of charge is not changing in time, it's just moving around. So Q is not a function of time. But the electric dipole moment will generally be a function of time, okay? Now, this first term is what we would have in the static case. We would have written this, but now we're allowing the electric dipole moment to vary as a function of time, okay? So we call this quasi-static. It's the same thing as the static potential, but it's changing in time. So the amount of dipole moment is changing in time, and that would mean, those field lines would shrink or grow in the same way that we have of a dipole field associated with the static two charges. But now the charges are moving, and this will move around. In addition, we now have a first order correction term, which depends on the current. Remember, a changing dipole is current, okay? So the current in the system contributes to the scalar potential, okay? And to lowest order, it's this, okay? Now, these terms, quasi-static radiation and induction, will become defined in a moment. Quasi-static, we just define radiation and induction, okay? All right, so this is the first order expansion of this. Similarly, we can look at the vector potential and keep the same terms only to first order in x prime, just as we did over there for the scalar potential. Now, you may or may not remember that when we did this in magnetostatics, this first term was the magnetic monopole moment, which was 0, okay? However, in statics, that's not the only thing that this contributes to. So, boy, I can get through so much lecture this week, This is totally bad way of teaching, sorry. This integral here, we could rewrite using integration by parts as the gradient should have a prime. God knows how many years I've had these notes that I've never noticed that, but anyway. Because when I put that on the other side, I get this, right? And then the divergence of J for statics was 0, but for dynamics is related to the rate of change of the charge density, okay? So these minus signs cancel, and then I get the integral of the position of the charges times the charge density time derivative, which is the derivative of the electric dipole, which is current, okay? So the vector potential here, the lowest order is this, okay? Yeah.
Why is the charge density evaluated at T naught rather than the entire retarded time?
Good question. The reason is that we've done this Taylor series expansion, okay? So let's go back to here in the notes. So what we did, to remind you, is we took the retarded time and wrote it approximately in this way, okay? And so what that gives us in these various expressions, I might have rho at t retarded is approximately equal to rho at t naught plus r hat dot x prime over c, okay? Just expressing that in, okay? Then, if this is small compared to this, then this is approximately
And in taking the Taylor series expansion, we're saying it's small, sufficiently small that we can do this?
That's correct.
Okay.
So that's absolutely important. So we made this expansion. We said what it is that the retarded time is equal to what the retarded time is at the origin plus a small correction.
Okay.
And so all of this is predicated on these approximations, that these both I'm far away compared to the size of the sample, And secondly, the distribution of retarded times is small compared to the retarded time to the origin. And those conditions are there somewhere. Okay, good.
So isn't it like Fourier series expansion of both variables?
Which variables are we talking about?
Position and time?
In some sense, position and time, right? So we said that in this sense, we expanded 1 over r in this way.
And then the retarded.
And also that the retarded time difference is small, the distribution. So there's an overall retarded time from the origin all the way to me, and there's a small change in the retarded time. And that allows us to do that Taylor series expansion. Both of those are happening. And they happen here. So this was the 1 over r term, and this is this. Very good. Okay, so given that, we can then, given the potentials, we can find the fields. Okay? So the fields are given by the gradients and derivatives of the potentials. And this is the vector potential, so this term comes from here, and then I have to take the gradient of the scalar potential, which is a mess, but you know, you use all your Einstein summation convention, which I know you love so much, and at the end of the day, you take it out of the oven, and it's a perfect chicken. No, it's this. So, yeah, so let's see, what do we see here? What's the top term?
Dipole plus monopole.
Right, so this is the electric field of a monopole. And this, if this was not a function of time, we recognize this from exam 1 as the electric field associated with an electric dipole, okay? But now, this is changing as a function of time. So again, that, you know, picture I'm drawing in your head of what the electric field lines is, if the dipole is changing, this would change, but the form is exactly the same. This is the quasi-static. It's also called the near field solution, for reasons that I'll emphasize in a moment, okay? Then we have something that looks kind of similar to this, it's just the time derivative of that. And then we have a third term that isn't exactly the same. It doesn't have this factor of 3 in it. And it has a different sign, but that's kind of not so important. But what is important here is the dependence on R, okay? So if I am extremely far away from the sample, which of these terms is going to dominate? The radiation. This is what's known as the far field, or the radiation zone, or the far zone, not the twilight zone. I'm extremely far away from the source, and we'll have to think about what that means compared to what, because we can never say big. Everything is always a comparison between two things, always. Then this term dominates. And one of the things to notice here is that radiation depends on the second time derivative, okay? It doesn't depend on the current, but the change in the current, the time rate of change of the current, is what's giving rise to this field, which is what we're going to call electromagnetic radiation. Whereas this is the static zone. This is the near field, and then there's the intermediate zone. Okay. Okay. In addition, we have the expression for the magnetic field. The magnetic field is the curl of the vector potential. And the vector potential, we said, was just the lowest non-vanishing order was the current over R. So I take the curl of that and I do, the chain rule and all of that. Then I get this expression for D. Okay. Again, when R is extremely big, I see that this term dominates. This is the radiation term. It's the magnetic field associated with the electromagnetic wave. That's the complement of the electric field. And then we also have an induction term. Notice there's no near field in this case. Why not?
Just there are no magnetic monopoles.
Yeah, it's sort of related to that point. We only took terms up to a certain order here. We only took the terms that were up to this lowest order in x prime. And the lowest order in x prime terms gave rise to things that depended on the electric monopole and the electric dipole. There's no magnetic monopole term, but interestingly, the magnetic dipole term doesn't contribute in this order. The dominant effect in the magnetic field is due to the oscillating current coming from the electric dipole. There will be a magnetic dipole term, but let me ask you, in the quasi-static regime, how does the magnetic field fall off as a function of distance for a magnetic dipole? For a magnetic dipole, the magnetic field. 1 over R cubed, right? Just like for an electric field, the field. Remember, for a monopole, the fields all fall off like 1 over R squared, and for a dipole, the fields fall off like 1 over R cubed. That's why it doesn't appear. There will be, as we will see next lecture, when we talk about magnetic dipole radiation, a term that would be quasi-static, it goes like 1 over R cubed, and then a radiation term there, but it will be smaller. So the dominant effect, the lowest non-vanishing order, is related to the monopole, electric monopole, and the electric dipole. The magnetic dipole and electric quadrupole come in the next order. All right? Okay, I'm gonna get out my cheat, I'll stop my cheat sheet soon. I wanna just sort of look at this expression. So, I just said, let's imagine we have some overall charge distribution that's neutral. But the charges might separate and I can have some oscillating electric dipole or changing electric dipole. I just want to look at the scales again of things, all right? So, if we looked at what our electric field, we had the quasi-static electric dipole term, which fell at 1 over R cubed. We had this induction zone, which fell off like 1 over R squared, and then we had the radiation field, which falls like off like 1 over R. So again, if I think about just in terms of scales, let's say P dot is some overall amplitude over some time scale. Okay, so if 1 over T was like omega, we'd say like P dot is like omega P, right? As I was just saying. So now if I look at what the electric field is and I factor out a P over R cubed to have this term, a term that grows like R over this distance, and a term that grows like R over that distance squared. And I have if this were an oscillating field, then as we said, CT is just lambda. And so what we see here is the contributions of these different terms to the electric field depends on how far I am away from the source compared to the wavelength, okay? That's different from how far away I am compared to the size of the source. I'm assuming I'm for sure far compared to the size of the source. If it's an atom, I'm far compared to a few angstroms, for example. But I'm somewhere different. I might be close compared to a wavelength or far compared to a wavelength. If I'm looking at, nanophotonics, it might be right near the surface, or I might be far compared to the surface, compared to the wavelength. Okay, so I see here that in the near field is where I am close compared to the wavelength. If I'm very close compared to the source, compared to the wavelength, I say I'm in the near field. And in the near field, the quasi-static, it looks quasi-static. It looks like the fields of the static fields, but they're just changing with time, but the nature of them, their shape, everything we know about them is like what we know from statics. On the other hand, if I'm very far compared to the wavelength, I'm in the far field. And there, it looks very different, okay? And here's my artist's rendition of the electric fields, and we'll come back, associated with an oscillating dipole, okay? So when I'm in the near field, it looks like the electric field associated with dipole. But in the far field, what we'll see is what we have here are field lines that fly away from this source. This is electromagnetic radiation. And that electromagnetic radiation is quite different in nature than the electric fields that are near. It's a complicated mess in between, and it doesn't actually process itself with little, they're just like, it's a cloud of uncertainty in the induction zone. How I get from here to here is very complicated. Okay. Very good. All right. So, just summarizing then, and the electric field that we saw associated with the radiation zone, the part that went like 1 over R, was this. And the magnetic field is that. Okay? Both of them depend on the second time derivative of the electric dipole moment. Both of them depend on the change in current. Okay? Now, there's a few different things to notice about this field. One is it falls off like 1 over R. We'll come back to that in a moment, why that's very important. But the other thing we notice is the vector nature of the field. Okay? So notice what is here. This is the vector minus this. Well, what is that? That is the component of the vector that's along R. So here's, say, the dipole moment. Let's say it's here. And I'm looking at it at some position along this direction. Okay? I can take this vector P and break it up into a component that is along R. I'll call that the longitudinal or parallel component, and a component of the vector that is perpendicular to R. The parallel component, well, it should be this times R hat, right? This times R hat is that vector. And P perp is the amount that's left over. So I take the vector and I subtract off the component along R hat, and that's what's here. Okay? whereas B is equal to the just R hat cross. What direction is B in, given this, assuming that P double dot is along this direction?
Into the board.
Yeah, into or outer, depending on the sign of this. P cross R is into the board. So let me draw a little picture over here again. So, it's drawn here, and then so if P double dot is in this direction, the electric field is perpendicular to the direction of propagation. It's in the plane of R and P and perpendicular to R, okay? And B is perpendicular to both of them. So said another way, I have the following. Let's consider R hat crossed into using the old back minus cab rule. Okay, and this is what we call P parallel. This thus is equal to P perp, or P double dot. The part that is perpendicular to the direction of that I'm looking at, which is also equivalent to the direction of propagation. Okay. And so what we have here is that this is equal to this, and let's double check. If I look at R crossed into this, well, that's equal to R crossed into P double dot, and then R cross that is 0. Okay, so what we have in these two expressions is this is E and this is B. All right, let's go back to the board. Enough of that. It's too hard to concentrate and pay attention to all that. Okay, so what we have is that in the far field, when R, the distance from the origin to the point of observation, is much, much bigger than lambda, or C times T, then we had that the electric field associated with the radiation at my point of observation was equal to let's examine that for the specific case. So let's say that we have that, suppose, let's use a different word. That my dipole moment is oscillating as a function of time with some frequency, okay? So that could be, I have two charges that are moving back and forth with one another such that the amplitude of the oscillation is oscillating cosine omega t, okay? Which I could also write as the real part of P naught e to the minus I omega t. Either way. Okay. What is the electric field thus associated with the radiation associated with an oscillating dipole? Right, so now we can just say that, let's look at the complex amplitude of the radiation. So I'm going to write this ooh, we have to be very careful. Okay, so what did I do? I just looking at this, I plugged in the second time derivative there. I got a minus omega squared. And then I'm only looking at the perpendicular component of this vector. And I evaluated the time at the retarded time. What would you say about the nature of this electric field?
Oscillating.
It's oscillating. What kind of wave is it? Is this a plane wave? It's not a plane wave, it's a spherical wave. How do we know it's a spherical wave? Falls up 1 over r. This is a spherical wave. The amplitude falls off like 1 over r. Moreover, the surfaces of constant phase are spheres. Everything, a point of observation that is a certain distance away, no matter what theta or phi is, it has the same phase, right? So everything on a sphere, a distance r from the origin, has this phase. And what is that phase? That phase is the phase accumulated over the retarded time. You see how I got from here to here? The excess phase, I can write this as e to the minus. That's what this is. So there's an oscillating dipole, and what I see at my thing goes up and down, but the phase of the oscillator is not the same as the phase of the oscillator over here, because it took time for that to get. And the phase at my point of observation is the phase accumulated over the retarded time. That's what a wave is, okay? It's a propagating disturbance, and the reason it has this spatio-temporal relation is because of the retarded time. That's what this is. That's why it's a minus there, because it took time. What I see at my point is what had happened in the past. at this earlier time. Yeah.
To me, this seems like it falls out just from the nature of time goes one direction and it takes time, not necessarily from retarded time.
But the retarded time is, it's a fact that what I see at my position is not the thing that happened at my time, but at an earlier time.
Yeah, I can say that even if the time were,
That's what the retarded time means.
oh, no, I see.
That's what it means. It means what I'm seeing at my time is not what the signal is instantaneously over there, but what it was in the past, because it took time for that signal to get to me. And that's why this has this form. Okay? So we have the retarded time and the spherical wave. Now, what about the amplitude of the wave? It falls off like 1 over r, but then we also have this, right? And that means what? Well, this was equal to, you know, P naught minus which is to say that from what we were just saying over here, from these differences, this is not an isotropic wave. So that is to say that although the wave front, the phase of the oscillation is the same on all points on the sphere, the amplitude isn't the same at every point on the sphere because our perp, or P naught perp, depends on the direction of observation compared to the direction of oscillation. So if this is P naught, right, and this is R, and let's call this the Z direction, then we can ask ourselves, what is this amplitude? Okay? Well, let's see how I want to say this. Right. So let's see. What is R cross P naught? R cross P naught is R cross Z hat times P naught, which is what? That's theta hat. Okay. And the distance, so this is sine theta hat P naught R cross, I'm sorry, what am I talking about? That's phi hat. So R cross that is phi hat, yeah. And then R cross P naught is sine theta. R cross that is theta. So what we have from all of that is that P perp, there's many ways of getting this, is equal to P naught sine theta phi hat, which is the electric field here. And the magnetic field So again, if I draw this picture over here, we have the electric field is like this, and the magnetic field is into the board. And this is R hat. It's, again, on the surface of a sphere. So at every point on that sphere, the electric field is different. The magnetic field is also different in the azimuthal direction. It's going in a circle around here. And the amplitude, how strong the field is, depends on theta. What is the amplitude when theta is 0? 0. It's maximum when I'm looking transverse to the oscillation. This is a transverse wave. I mean, the oscillating fields are transverse to the direction of propagation. What is the direction of propagation? How would we find it? Well, we can find it by seeing how energy flows by calculating the Poynting vector. It is propagating spherically outward. Absolutely. Those are, you're absolutely right, Benny. I can just think about it as the rays are perpendicular to the wave fronts. That's a perfectly valid way of thinking about this. All right. And if I just think about the radiation terms of this, I can then ask what is the intensity by looking at the time average. And what do I get? Well, I'm going to get something that looks like C over 8 pi. I'm going to get a k to the 4th, a p naught squared, a sine squared theta, and then I get theta hat cross phi hat is equal to r hat over r squared. Okay? So what we see here is the intensity of the wave is falling off like 1 over r squared in the spherical wave. And the intensity I see depends on where I'm looking relative to the direction of oscillation. With 0 intensity, if I'm looking along the direction of oscillation, and maximum intensity if I'm looking perpendicular when theta is pi over 2. Okay? So if I wanted to ask, if I have a sphere of radius r, and I want to know how much power flows through a little area dA on that. Okay. dA over here is r squared times the elemental solid angle. Okay. So the power radiated through a patch on the sphere is equal to the intensity times the area of that patch times the normal. Everyone with me? which is equal to, in this case, C over 8 pi k to the 4th p squared sine squared theta. Okay. Importantly, what we see here is this is independent of R. Yes?
You said the intensity was the time average pointing vector
Yes.
times the patch?
No, the intensity is the power per unit area. The power
Okay.
is the intensity times the area. So this is how many watts flow through this patch. But again, I want to emphasize it's independent of R. That's to say, no matter how big R is, there's this amount of power that flows through the area, even as R goes to infinity.
A is also.
It's fine. But I'm saying no matter how big or far away is, there's a certain amount of power that goes through this solid angle, this piece of 4 pi, no matter how far away I am. Which is to say that energy flows away or radiates to infinity. That's not true for the quasi-static or the induction zone, because those Poynting vectors would fall off faster than 1 over r squared. And so the amount of power would decrease with r. And as you remember when we did those problems where we took the cylinder and we moved it around and we got to go up, the energy went out, but then we can get the energy back, right? We can make the thing flow. That energy was sort of still attached to the charges, whereas the radiation flies free from the nest and flies away to infinity. Now, the amount of power is different at different distance. So from over here, there's no power that goes in this direction, but there's a lot of power that flows in that direction. Now, I want to show you a way to visualize it. So let's go back to our.
So we're still thinking of some changing charge distribution.
That's correct. So we're in this particular case, the particular example we just looked at, the charge distribution was 2-point charges that were moving relative to one another. We had an oscillating dipole. And that was the specific example we just looked at. We had 2 equal and opposite point charges, and they were oscillating back and forth. Okay, I love this. So this is a GIF, which is thinking about a point dipole that's oscillating. And you notice how the fields eventually kind of bud off from the charge stream. They're kind of connected to it in the near phone, but eventually there's this weirdo, induction zone stuff that's happening. And the field becomes its entity unto itself, somehow unconnected. It kind of takes on a life of its own. And if I'm sitting here, I see the electric field lines going up and down, that's the electromagnetic wave, okay, that I'm seeing. But the phase of that oscillation depends on what the phase of the oscillation is. In the near field, like right there, you see the dipole pattern, but then eventually it radiates away. Notice here, the strength of the field depends on theta. It's bigger in this direction, and it's 0 in that direction. okay? So it's a spherical wave, but it's an anisotropic spherical wave, meaning the amplitude depends on theta, okay? Very cool. Right, so just to conclude then, I want to show this picture. So our notes. Right. So this is what we just had for, these were the waves that we just discussed, right? This is the radiation. One way I like to think about this is that, if I just thought about 1 point charge, that 1 point charge would have, if it was static, it would have electric field lines going out from it. What happens if I shake that point charge up and down? If I shake that point charge up and down, I have an electric dipole moment that's changing as a function of time. And I can think about the wave that's generating just like waves on a string. I like to think about it as there's electric field lines shooting out from the charge at the speed of light. And if I move it up and down, I'm going to cause waves on a string that are going to propagate out at the speed of light. Now, I can't push on the string along that direction, so I'll have no waves generating along the direction of oscillation, and the maximum wave, you see that's what my picture of this amplitude is, will be different. This is a nice picture of what's going on, just thinking about waves on a string. Right, okay, so the final thing we had this, the power per unit solid angle was this, okay? This is what's known as a dipole radiation pattern. Often you will see this drawn in this way, meaning this is a picture which the length of this lobe depends on how much power I get per solid angle in that direction. So it's a long vector over here, and as I go around, you'll see, have anyone ever seen this kind of pattern? Like, you know, this, yeah, this is just a way of writing this sine squared function as a function of theta, where the length of the thing depends on the power per unit solid angle. Okay, that's a dipole radiation pattern. Okay, and if we were to integrate this over all directions, I ask, what's the total amount of power radiated? Time, you know, so I take the intensity, and I say how much power is radiated into 4 pi steradians. So I take this power per unit solid angle and integrate over all solid angles. You integrate sine squared theta over all side angles, you get 8 pi over 3. And so what we find is that the power radiated is proportional to k to the 4th, which is proportional to omega to the 4th, times the amplitude squared. The fact that it depends on omega to the 4th is very important. It means that things that oscillate much faster radiate a lot more, okay? And we'll pick this up next time, but I want to just say this last point was right here. As I was saying, suppose I have a charge moving in some trajectory. Okay? It could be going in a circle. It could be going up and down. It could be doing the loop-de-loop. Okay? And I want to know, what is the radiation to lowest order generated by that moving charge? Well, all I have to do is calculate the electric dipole moment. The electric dipole moment is the position of the charge times the charge. Everyone clear on that? So according to the formula we derived, the radiation is dependent on the second time derivative, which is this. Which is to say that the radiation is proportional to the acceleration of the charge. Accelerating charges radiate. Okay? And the power, that's the total amount of power that's radiated at some instance of time, is given by this formula where we do all those integrals. This is known as the Larmor formula. Okay? So an accelerating charge radiates. And the amount of power that's radiated is proportional to the square of the acceleration. The electric field is proportional to the acceleration. The power is proportional to the square of the field. It's proportional to the square of the, right? And the acceleration is the second time derivative, which means if I had an oscillating charge, the acceleration proportional to omega squared. So the power is proportional to omega to the fourth. Okay. So this is the summary of electric dipole radiation. In your homework, you have a problem that's just like this, but instead of having the charge go up and down, it's going in a circle. But the ideas are all the same. You just have to think about it. All right. Very good. Is there anyone who came in late who didn't get their exam? You can come over and finish. Very good. Have a good rest of your day.